Hey, all you buddies. We're going to talk about functions defined on surfaces and how we would use the chain rule for two independent variables, but also three intermediate variables. And that's like, you're like, whoa, Miss Stein, that's a lot of variables. Calm down. All right, so let's try and visualize what we're talking about here. So suppose W is some function of x, y, z, and potentially it represents some temperature at this point, this position on the surface. So we'll think about it as the temperature on the Earth's surface. So we may prefer to think of each of these x, y, and z functions, each of them as a function of the variables r and s, where maybe r and s give the longitude and latitude. So they're also helping with position. So we've got x is g of rs, and y is h of rs, and then z is k of rs. It's a funny looking r. So now we can think about W not as a point on the surface, but a point that we locate using longitude and latitude for each x, y, and z. Or we could think about this as being W is the temperature. We've got G of RS, H of RS, and K of RS. So this is the type of situation that we are looking at taking the derivative of to find that instantaneous rate of change, the rate of change in temperature at that specific spot or location. Okay, so this is the type of function we are dealing with. T is defined as x, y, and z, where x, y, and z are each functions representing longitude and latitude. So two independent variables and three x, y, and z intermediate variables. All right, so let me pull the definition in. So supposing that W is the function of x, y, and z, and x, y, and z each have two independent variables, r and s. So all of these functions, w, x, y, and z, all four are differentiable. And w has partial derivatives with respect to both r and s. And in an effort here to help us think about what is going on and how this function is defined, I've brought in these pictures. So this first piece is representing how that composite function is made. You know, we've got these two independent variables, r and s, and they each belong to g, h, and k, creating these three intermediate variables. So I've got x in terms of r and s, which we call g, y in terms of r and s, which we call h, and z in terms of r and s, which we call k. And so x, y, and z together, they are my function, which makes up w, my dependent variable. And so these are two dependency diagrams here. The first representing the partial with respect to r, and the second representing the partial with respect to w. And I would just encourage you to pause and think about what's going on here, and that will help you remember how to set these equations up, these formulas, or to use the formulas, I should say. So for the next problem, we're going to work an example here on this next slide. So for this example, we are going to find the partial of w with respect to r and the partial of w with respect to s. Each needs to be in terms of r and s respectively. So W is a function of three variables, and each of these three intermediate variables is a function of two independent variables. We've got R over S, R squared, plus ln S, and 2R. So let's start first by finding partial W with respect to R. And I've pulled in our formula, which we just defined on the previous slide. So that means I need the partial of W with respect to X, with respect to Y, and respect to Z, and then the partial of each X, Y, and Z with respect to R. So these are going to be partials of each. So I prefer, as we work through these problems, I prefer to think about doing each partial individually. I do my scratch work for each one, and then I just pull it all together. So that's what I'm going to do here. So first, partial of X with respect to R. That means S is a coefficient. So this is like saying 1 over S times R. That partial is 1 over S. All right, partial of Y with respect to R. That means S is a constant. Natural log of S is a constant. The derivative of that's 0. And the derivative of this is going to give me 2R. And last, partial of Z with respect to R will be 2. All right, so we have those three pieces. I've got my X, Y, and Z partials there. So now I need to take this function, W, and take the partial with respect to X, Y, and Z as well. So let's see, partial of W with respect to X, that means Y and Z are constants, we'll get 1. Partial of W with respect to Y, that's going to give me 2. And partial of W with respect to Z is going to give me 2Z. So I've got 1, 2, and 2Z. So if I set this up then, dW dx is 1 times 1 over S plus 2 times 2R plus 2Z times 2. So that means dW dr is 1 over S plus 4R plus 4Z. Now, we want this partial derivative to be in terms of my independent variables, R and S. So I have this Z. So we need to say, well, what is Z in terms of R and S? So scrolling back up, we have that Z was given as 2R. So 4 times 2R, that's going to give me my partial of W with respect to R is 1 over S plus 4R plus 4 times 2R, which is 8R, and 8R plus 4R gives me 12R. So that's my first part of the question. So the second, I need to find partial of W with respect to S. So I'm going to pause, erase this, and go back up to the top and start over. Okay, so right before I erased all of that, we found partial of W with respect to R. Now we're going to find partial of W with respect to S. So I need each of these three partial derivatives of my intermediate variables with respect to S. And then I'm going to take the partial of W with respect to X, Y, and Z. So first, finding the partial, each of these with respect to S, each of my intermediate variables. So partial of X with respect to S. Well, S is in the denominator, R is a constant. We could think about this as being the same as R times S to the negative 1. So that's going to give me negative R S to the negative 2 when I differentiate with respect to the independent variable S, or rather R, negative R over S squared. All right. Partial of y with respect to S, that means R squared is a constant, and the derivative of natural log of S is going to be 1 over S. And the partial of z with respect to S, 2r is a constant, and the derivative of a constant is 0. And of course, in the first part, we found each of these partial derivatives, but partial w with respect to x was 1. Partial w with respect to y was 2. And partial w with respect to z was 2z. So using our formula and these 6 pieces that we found, we can write the partial of w with respect to s. So partial w, partial s, is we have 1 times negative r over s squared plus 2 times 1 over s plus 2z times 0. So 2z times 0 goes away, and I will simplify this. Partial w respect to s is negative r over s squared plus 2 over s. And that's my final answer. So if f is a function of 3 intermediate variables, and each of those intermediate variables are functions of 2 independent variables, r and s, then this is how we could find those partial derivatives. Let's do one more example, and I suppose if you really understand that first example, then you could skip this because it's going to be pretty redundant. But what we're going to suppose is that w is a function of 2 intermediate variables instead of 3. So it's just basically a shorter version of what we just did. So x and y, each of those are functions g and h of 2 independent variables r and s. So make sure you're noting that I'm saying intermediate versus independent. And essentially, we're just going to lose that third term. So our example is we have a function of 2 variables, 2 intermediate variables, and then x and y, those intermediate variables, are functions of 2 independent variables. And we want to find partial of w with respect to r and partial of w with respect to s. So I'm going to do my scratch work first. Partial of w with respect to x is 2x. Partial of w with respect to y is 2y. All right, so partial of x with respect to r is 1. Partial of x with respect to s is negative 1. Partial of y with respect to r is positive 1. And partial of y with respect to s is also positive 1. So I find all of those partials, then I can say dw dr, so that's partial of x or partial of w with respect to x, 2x times x with respect to r, which is 1, plus the partial of w with respect to y, which is 2y, plus the partial of y with respect to r, which is 1. So we end up here with 2x plus 2y. That's my partial of w with respect to r. Similarly, partial of w with respect to s. So I'm still going to have that 2x and the 2y, but the partials of my intermediate variable functions, those are going to be with respect to s. So I've got -1 and +1 here. So this simplifies to -2x plus 2y. So we're not quite done yet. We found those partials, but we want to make sure we're paying attention. We want them in terms of r and s. And my two partials here are in terms of x and y. So we just need to plug the fact that x is equal to r minus s and y equals r plus s. That was given. X equals r minus s, y equals r plus s. So partial of w with respect to r is 2 times r minus s plus 2 times r plus s, which simplifies to 4r. So that is my partial of w with respect to r. And my partial of w with respect to s is -2 r minus s plus +2 r plus s. Simplifying that, I get 4s. And now we're done. All right, so that was just an extra example to show you guys how we use this rule. Okay, we can use it with less intermediate variables. I hope you guys are feeling great about this topic. Please email me if you have any questions. We have one, maybe two more videos, I think just one in this series, where we're going to talk about implicit differentiation again. We're going to kind of revisit it and redefine it. Have fun, be safe.